For our lesson 3 in chapter 1, we will discuss the matrix operations and their properties. Matrices are usually represented by capital letters or by a representative element enclosed in brackets such as this, or they can be represented by a rectangular array of numbers such as this one. Now, for the equality of matrices, we have two matrices A and B are equal when they have the same size, say m by n, and each corresponding element Aij and Bij are equal. For example, consider these matrices A, B, C, and D. Observe that A and B are not equal since they are of different sizes. Also, notice that A and C still have different sizes, so they cannot be equal. However, if we try to look at matrix A and matrix D, we see that both are 2 by 2 matrices. And these elements here, 1, 2, and 4, are equal. So we say that A and D are equal if x is equal to 3. Next, we take note of the term column matrix or column vector, which refers to a matrix that has only one column. An example of which is this matrix B. Moreover, a matrix that has only one row is called a row matrix or row vector, such as this matrix. We have matrix C. Boldface lowercase letters often designate column matrices and row matrices. For instance, matrix A can be partitioned into the two column matrices. We have A sub 1, which is equal to the 2 by 1 matrix containing 1, 3, and we have here A sub 2 equals this one. So we can express A as this. Now let us proceed with the operations on matrices. First, we have the matrix addition. If A and B are matrices of size m by n, then their sum is the m by n matrix given by this, where we simply add the corresponding elements of A and B. Note that the sum of two matrices of different sizes is undefined. Next is the scalar multiplication. If A is an m by n matrix and C is a scalar, take note a scalar is a quantity that is described by a numerical value. Then the scalar multiple of A by C is the m by n matrix given by this one. That is, we multiply each element of matrix A by C. We will have the examples of these operations later. Now we note that we can use negative A to represent the scalar product of A by negative 1. So if A and B are of the same size, then A minus B represents the sum of A and the scalar multiple of B by negative 1. That is, A minus B is equal to A plus negative 1 times the matrix B. Now, as examples, given these matrices A and B, let us find first the scalar multiple of A by 3. We have A is equal to 3 times the given matrix A. We have 1, 2, 4, negative 3, 0, negative 1, 2, 1, 2. Which is equal to, we just simply multiply each of these elements here by 3. So we will have 3, 6, 12, then negative 9, 0. Again, we multiply this by 3. We have negative 3, 6, 3, and then we have 6. So this is 3 times A. Next, we find negative B. which means we will multiply the scalar -1 to matrix B so that we have uh, -1 times the matrix B. We have 2, 0, 0, 1, -4, 3, and then -1, 3, 2. Okay, so again, just simply multiply these elements here of the matrix B by -1, so we get -2, 0, 0, -1, 4, -3, then 1, -3, and then -2. And for the third one, we solve for 3a minus b. So we simply add 3a and the negative b. We have we have 3a minus b equals 3, 6, 12, -9, 0, -3, 6, 3, 6, and then plus the negative b, which is negative, sorry, with 6 plus -2, 0, 0, -1, 4, -3, 1, 3, -2, which is equal to, we have 1, 6, 12, we have -10, 4, and then -6, we have 7, 0, and then, sorry, that's 4. Okay, so we just simply add the corresponding elements of these two matrices. So the A11, the A12, and then A13, and so on. So we get this 3A minus B. So we have again these solutions for the given problem. The next operation is matrix multiplication. So if A is an M by N matrix and B is an N by P matrix, then the product AB is an M by P matrix. This means that you can only multiply those two matrices if the number of columns of the first matrix is equal to the number of rows of the second matrix, which is the multiplier. So we have here this n must be equal to this one here. Okay, so for example, if you have a 2 by 2 matrix, then the multiplier must be a 2 by something matrix. The product of these two matrices A and B is equal to the matrix with elements Cij, where Cij is equal to the sum of AI AI1 times B1j plus A12 times B2j, and so plus and so on until A sub in times bnj. This means that to find the entry in the ith row and the jth column of the product AB, multiply the entries in the ith row of A by the corresponding entries in the jth column rather of B, and then add the results. To make this clear, let us solve this next example. Find the product AB given these matrices A and B. Before we proceed with solving this product, we first check if this product is defined by looking at their sizes. So since A is a 3 by 2 matrix and B is a 2 by 2 matrix, then we can multiply these two and their product must be of size 3 by 2. So we have A times p is equal to, we have negative 1, 3, 4, negative 2, 5, 0, multiplied by, we have negative 3, 2, negative 4, 1. Okay, so again, this is a 3 by 2 matrix, and this one is so we have, this is a 3 by 2, and this one is a 2 by 2 matrix. So the product is defined since we have here the number of columns of the first matrix is equal to the number of we have rows of the second matrix. So its product must be a 3 by 2 matrix. So that should be the product. Okay, so to multiply, we multiply the first row of A, this 2, which is this one. So we multiply this first row of A by the first column of B and add the results to get the A11 entry of the product. That is, we have negative 1, we multiply by negative 3, and then this 3 here should be multiplied by the negative 4 here. So that will be our first entry for the product. Next is, for the A12 entry, we multiply this first row of A by the second column of B. So we have negative 1 times 2, then add by 3 times 1. Okay, so we have, again, the result must be a 3 by 2 matrix. So we have the first row. Next is, to get the A21 entry, we will multiply the second row of A by the first column of B. So we will have 4 times negative 3 plus negative 2 times negative 4. To get this entry here, which is the A22, we will have to multiply again this second row by the second column of B. So we have 4 times 2 and then plus negative 2 times 1. And then for the third row, we will multiply the third row of A times the first column of B. 5 times negative 3 plus 0 times negative 4. And then for the last entry, we will multiply the third row of A by the second column of B. So that is 5 times 2 plus 0 times 1. Okay? Actually, you can do it in a scratch paper, or you can do it in your mentally. To get the result, we have, this is positive 3 minus 12, so that is negative 9. And then this one is, we have negative 2 plus 3, so that is 1. Then negative 12 plus 8, so that is negative 4. Next is 8 minus 2, so that's 6. This one is negative 15, this is 0. And then this one is 10, and then this one is 0. Okay, so the answer is this one. So this is the product AB. Now next, so given these matrices A and B, calculate A plus B and B plus A. Now the question is matrix addition commutative? Can you prove or disprove it? Also, solve for the products AB and BA. Is matrix multiplication commutative? So I will leave this to you as an exercise. Next, let us have some more examples for matrix multiplication. So the first one, observe that the first matrix is a 2 by 3 matrix and the other one is a 3 by 3 matrix. So therefore, the product is defined and the resulting matrix must be a 2 by 3 matrix. So let us write the given first. So we multiply the matrices 1, 0, 3, 2, negative 1, negative 2 multiplied by have negative 2, 4, 2, 1, 0, 0, negative 1, 1, negative 1. Okay, so again, this is a 2 by 3 matrix multiplied by a 3 by 3 matrix. So that implies that the product must be a 2 by 3 matrix. So this one is equal to, again, we first multiply the first row of the first matrix by the first column of the second matrix. So this, multiply it by this. And then after multiplying, we add the results. So we will do it mentally. So we'll have here, this one is negative 2, and then 0, and then negative 3. So it's negative 2 plus negative 3. So we have negative 5. And then next is for the next entry, we multiply again this first row here by the second column of the second matrix. So that's 1 times 4. So that's 4. Then we have 0 and then we have 3. So that's 4 plus 3. We have 7. Next is we multiply this first row to the third column of the second matrix. So 1 times 2, we have 2. Again, we have 0 here, and then we have negative 3. So that is 2 plus negative 3. So we get negative 1. And then for the second row of our resulting matrix, remember we have a two rows for the resulting matrix. So for this row, we multiply the second row times the first column. So we have that's negative 4 and then negative 1. So that's negative 5. Multiply this, that's 2. So we have negative 3. And then again, we multiply this second row to the second column. So that's 2 times 4, that's 8. This is 0 minus 2. So that is 6. Then for the last entry, we have 2 times 2, 4. Again, that's 0. And then that's positive 2 rather. So we have 6. Okay, so this is now the product of these two matrices. Okay, next. Next, we have this 2, negative 1, 1 multiplied by 1, negative 2, negative 3. Okay, so again, try to see first if the product is defined by looking at their sizes. So this one is a 3 by 1 matrix multiplied by a 1 by 3 matrix. Therefore, the resulting matrix or the product will be a 3 by 3 matrix. Okay, so we multiply these two. So we have here a 3 by 3 matrix. Sorry. Okay. So first is we multiply the first row by the first column. So we have 1 entries only. So that would be easier. So this one we have 2. And then next, this first row we multiply by the second column here. So that's negative 4. And then this row multiplied by the third column. So we have negative 6. Next, for the second row, we multiply the second row here by this one. So that's negative 1. The next, we multiply this negative 1 by negative 2. So that's positive 2. Negative 1 times negative 3. So that's positive 3. And then for the third row, we multiply this third row here of the first matrix times the first column of the second matrix. So we have 1. And then we multiply 1 by -2, so it's -2. 1 times -3, so that is -3. So we have the product of these two matrices, we have this one. And for the third one, we have, so we multiply 1, 2, 1, and then multiply by -1, 2, 1, -1. Okay, so take note of the sizes first. So this is a 2 by 2 matrix and another 2 by 2 matrix. Hence, the product must be a 2 by 2 matrix. So we multiply this. Again, the first row first multiplied by the second column. So that is, we have 1 and -1. So that's -1 plus 2. So that's 1. Next is this first row multiplied to the second column here. So we have 2 and then -2, so that is 0. Then this second row multiplied to this first column, so that's -1 and 1, so that's 0. Then again, this multiplied by this one. The 1 times 2, that's 2, and then plus -1, so that's 1. So the result is this matrix. Okay, so those are the examples of matrix multiplication. Now we have an application of matrix multiplication. This is representing a system of linear equations. This system can be written as the matrix. This system can be written as the matrix equation Ax equals B, where A is the coefficient matrix of the system and X and B are column matrices. For example, we solve the matrix equation Ax equals 0, zero vector, where given the following. We have here the A and then the column matrix corresponding to X, and then we have the 0 vector. So as a system of linear equation, this matrix equation Ax equals 0 can be written as x sub 1 plus, that should be x sub 1 minus 2x sub 2 plus x sub 3 equals 0, and 2x sub 1 plus 3x sub 2 minus 2x sub 3 equals 0. So that the augmented matrix of this system is given as, we have 1, -2, 1, 0, 2, 3, -2, 0. So this is the augmented matrix of this system. Now let us solve the system by applying Gauss-Jordan elimination to this matrix. So recall, so what we need is, we want this to become 0. So what we do is we multiply the first row by -2 and then we add it to the second row. So we will have here R1 plus, that's R2 plus -2 of R1, then to yield new R2. So we copy row 1. So again, we multiply by -2 and then we add it here. So we will have 0. We have multiply this by -2, so that's 4, so that's 7. Multiply by -2, so plus -2, so that's -4, and then we have 0 here. Next is, we want this to become 1, so we want a leading 1 in the second row. So we simply multiply the second row by 1 over 7. So 1 over 7 times row 2 to get new R2. So that's 0, and then we have 1, negative 4 over 7, and then 0. Next is, we want this to be 0. We can have, we just copy the second row. Okay, to make this 0, we can multiply this by 2 and then add to this one. So that means we have R1 plus negative 2 R2 to get new R1. So this is 1, this is 0. Again, we multiply this by negative 2 and then we add it here. So that's negative 8 over 7 plus 1. So that's negative 1 over 7. And then this one is 0. Okay, so converting back to the system form. So this implies that we have x sub 1 minus 1 over 7, x sub 3 equals 0, and x sub 2 minus 4 over 7, x sub 3 equals 0. Hence, this system has infinitely many solutions. So we write it here. Note that a convenient choice of parameter here is x sub 3 equals 7t. So we let x sub 3 equals 7t, so that we have x sub 2, we have substitute 70 here. So we have x sub 2 minus 4 over 7 times 70 equal to 0, which implies that x sub 2 is equal to 4t. Also, x sub 1 here, x sub 1 minus 1 over 7 times 70 is equal to 0. This implies that x sub 1 is equal to t. Okay? Thus, we say that the given matrix equation has infinitely many solutions represented by this. Okay, so your x is equal to the column vector t, 4t, 7t. You can factor out t. So you have here t times 1, 4, 7, where t is any scalar. So that is any scalar multiple of the column matrix 1, 4, 7 is a solution. Now, sometimes it is more convenient to represent the system AX equals B by partitioning the matrices A and X. This is being done in the following manner. Now, if A is a coefficient matrix and X is the column matrix of unknowns and B is the column vector in the right side of the M by N linear system AX equals B, then we have this. And by multiplying these matrices, we get this one, which is equivalent to this. So in other words, AX is equal to x sub 1 times a sub 1 plus x sub 2 times a sub 2. Remember, your A there are the columns of the matrix A. So this expression is called a linear combination of the column matrices A1, A2, and so on up to AN with coefficients x sub 1, x sub 2, and so on up to x sub n. The matrix product AX is a linear combination of the column vectors A sub 1, A sub 2, to A sub n that form the coefficient matrix A. So these things here. Furthermore, the system AX equals B is consistent if and only if B can be expressed as this linear combination, where the coefficients of the linear combination are the solution of the system. Example, we write the column matrix B as a linear combination of the columns of A, where A is this and B is this one. So this means that we need to find the coefficients x sub 1, x sub 2, x sub 3 such that to find x sub 2 and x sub 3 such that we have x sub 1, sorry, 1, 3, then plus x sub 2, negative 1, negative 3, plus 2, 1, which is equal to negative 1, 7. So we express the column vector negative 1, 7 as a linear combination of the columns of A. Sorry, this should have x sub 3 here. Okay, so we can, again, we can express this as a linear combination of the columns of A if we can find this x sub 1, x sub 2, and x sub 3. So if we multiply this, we get the system of linear equation as x sub 1, x sub 2, x sub 3 equals negative 1, and 3x sub 1 minus 3x sub 2 plus x sub 3 equals 7. Thus, we have the matrix 1, negative 1, 2, negative 1, 3, negative 3, 1, 7 as the augmented matrix corresponding to this system. Now, let us use Gaussian elimination to solve the system, or we apply the Gaussian elimination here. So we have, okay, we want this to become 0, so we can have here, we can multiply R1 by negative 3, and then we add it to R2. Negative 3 R1 to get new R2. So we have here 0. We multiply by negative 3. So this is positive 3 plus negative 3. So that's 0. Times negative 3 here. So negative 6 plus 1. We have negative 5 times negative 3. So that's positive 3 plus 7. So that is 10. And we want this to have a leading 1 here. So this, we want this to become 1. So we have we multiply by negative 1 over 5 by R2 to get new R2. So it's 0, 0, then 1, then negative 2. So we have now a row echelon form. So we obtain the system. The system x sub 1 minus x sub 2 plus x sub 3 equals negative 1 and x sub 3 equals negative 2. Notice that we have one free variable, so we have infinitely many solutions. So with our x sub 2 as the free variable, so we let it as t. So if x sub 2 is t, so we get x sub 1 as, we substitute t here and then negative 2 here. So that is x sub 1 is equal to 3 plus t. And again, our x sub 2 is the t, and then x sub 3 is equal to negative 2, where t is any real number. So one solution of these infinitely many solutions, solution to this is, say, let's say t is equal to 1. So if t is equal to 1, we get x sub 1 equals 4, x sub 2 equals again 1, x sub 2 is equal to 1, x sub 3 is equal to negative 2. Thus, we can have the linear combination of this column vector. We have we have 4, 1, 3, then plus 1 times negative 1, negative 3, then plus, can have minus 2 here times 2, 1 equals negative 1, 7. So we have expressed B as the linear combination of the columns of A. Okay? So you can check your answer if you get it correctly. So you multiply this by 4, then minus 1, minus 4, so that's negative 1. 12 minus 3, minus 2, so therefore that is 7. Next, we have what we call a diagonal matrix. A square matrix, take note, a square matrix is called a diagonal matrix when all entries that are not on the main diagonal are 0. So for example, we have a 3 by 3 matrix, say 1, 0, 0, 0, negative 1, 0, 0, 0, negative 2. So this is a 3 by 3 matrix, a square matrix. And then we have the main diagonal. And then the rest of the entries outside the main diagonal are 0. So this one is called a diagonal matrix. Also, we have the trace. The trace of an n by n matrix A is the sum of the main diagonal entries. That is, trace of A is equal to the entry A11 plus A22 plus and so on up to ANN. Now let us do the following exercises. So first, we find the products AD and BA for the given diagonal matrices A and B. So A is equal to 3, 0, 0, 5, 0, 2, and then B is equal to negative 7, 0, 0. Okay, so again, notice that these two given matrices are diagonal matrices since we have zeros outside the main diagonal entries. Okay. So first we get the product AB. So we multiply a 3 by 3 matrix by a 3 by 3 matrix. So the resulting product is 3 by 3 matrix also. So since we want to multiply this first row here to the first column here, so notice the zero. So we will just multiply 3 by negative 7 since these two will just become 0. So that's negative. And also we have Next is the first row multiplied to the second column. So we got, this is 3 times 0, so 0, and then 0 here, and 0. So we will just have 0 there. Okay, and then we multiply this first row by the third column. So this 3 times 0, that's 0, then 0 here, also 0 here. So that is 0. Next is we multiply the second row to the first column of B. So that is 0, 5, negative 5 times 0, so 0, and then 0 also. Okay, then multiply this by the second column of B. So we have 0 and 0. So negative 5 times 4, that's negative 20, and then the last is 0 also. So we'll just have negative 20 here. Then the second row to the third column. So that's 0, 0, and then it's 0. Okay, and then since we have here the last row for A, we have all zeros here. So when we multiply and then add the result will be just 0. Okay, so we multiply this by this, we get 0. When we add the results, this one to this, we'll just get 0, and so on. Okay, so the product AB, we have this answer. So have you noticed that the product of these diagonal matrices AB is just a diagonal matrix whose main diagonal entries is the product of the main diagonal entries of these two matrices. So simply you can have 3 times negative 7, and then negative 5 times 4, that's negative 20, and then 0 times 12, so that is 0. So what about B, the product BA now? So when you multiply, we start with the matrix B multiplied by A. So your first step would be the first row of B multiplied to the first column of A. And also the first row of B to the second column, and then to the third row, and so on. Then you can do it, and then notice that you will just get also this matrix. Okay, so you will notice that your product AB is just equal to the product BA, which in fact, in general, if A and B are diagonal matrices of the same size, then the product AB and BA are just equal. Are diagonal matrices of the same size, then AB is just equal to BA. Okay, try to prove. So our next example is to find the trace of the matrix. So again, when we find the trace of a given matrix, we will just add or get the sum of the entries of the main diagonal. So that is, we have the trace of A is just equal to 1 plus 1 plus 1 plus 1, which is just equal to 4. Again, we simply add the entries of the main diagonal. Now next, in multiplying large sizes of matrices, sometimes it is helpful to partition the matrices into sub-matrices. For example, say we have matrix A and B partitioned into these 4 sub-matrices, then we can block multiply A and B provided that the sizes of these sub-matrices are such that the matrix multiplications and addition are defined. So the product A, B is just equal to A, the submatrix A11 times B11 plus A12 times B21, and so on. Okay, so we just simply follow the rule in multiplying matrices. So the first row here multiplied by the first column, and then first row again multiplied by the second column to get this entry here, and then the second row multiplied by the first column to get this one, and the second row rather multiplied to the second column to get the entry here. So let us have an example for this. So perform the indicated block multiplication of matrices A and B. Okay, so we let this, let's say A11, A12, and then this block here, let us name that one as A21, A22. This block here, we name that as B11, then B12, B21, and then B22. Now again, when we do the multiplication, we have here, we multiply them as blocks. So we have the first row multiplied to the second column. So that is A11 times B11 plus A12 times B21. Then for the second entry here, by the way, we consider this as a 2 by 2 matrix and also a 2 by 2 matrix. So therefore, when we multiply, we have a 2 by 2 matrix also. But remember that the entries are matrices also. So again, for this entry, we multiply the first row to the second column. We have A11 times B12 plus A12 times B22. And then for the second row of this product, we have, sorry, this should be A times B. So this row multiplied to this, we have A21 times B11 plus A22 times B21. Then the second row to the second column, we have A21, B12 plus A22 times B22. Now let us consider the sizes of these block matrices first. So remember, this is a 2 by 2 matrix multiplied by a 2 by 2. So this must be again 2 by 2 times 2 by 2. So that is a 2 by 2 matrix. Should be added to this A12 multiplied by this, also 2 by 2 matrices. So that is 2 by 2. So we can do the addition also since they have the same sizes. Next is 2 by 2 times. Okay, so note that is 2 by 2 times your B12 is a 2 by 1 matrix. So therefore the product must be 2 by 1. Also, A12 is 2 by 2 matrix multiplied by this 2 by 1. So again, we have 2 by 1 matrix. So you can do the addition also. And we have here a 1 by 2 rather, 1 by 2 multiplied by 2 by 2. So you will have 1 by 2 here, and then this is 1 by 2 multiplied by 2 by 2. So also we have 1 by 2. So we can do the addition also of these two matrices. And then we have the A21 again, the 1 by 2 matrix multiplied by 2 by 2. So this is A1 by 2, and then A22 is 1 by 2, and rather this is a 1 by 2 multiplied by a 2 by 1. So this must be 1 by 1 matrix. This is a 1 by 2 multiplied by 2 by 1. So that's 1 by 1 matrix. Okay. Since we have some zeros here, some zero matrices here, so it would be easier to solve since the rest of, or some of the block matrices will be just zero. So for example, we have again A11 multiplied to B11 plus the product of these two, which is the 0. So we can just simply multiply the A11 and B11 because again, the product of this and this will be just 0. So we multiply. So again, the result must be a 2 by 2 matrix. So the first row multiplied to the first column. So that's 1 times 1, and then plus 2 times negative 1, so that's negative 1. Then this multiply to this one, so that is 2 plus 2, so that is 4. And then 0, 1 multiplied to this, we have negative 1. And then this multiplied to this, we have 1. Okay, so that is a 2 by 2 matrix for our first block. And then this must be, the result here must be a 2 by 1 matrix. 2 by 1, so 2 rows and 1 column. So we have 2 entries here. So this A11 multiplied by B12, again this is a 0 matrix, so that is a 0. And then also this is a 0 matrix multiplied to this, so the result will be just 0. So we'll just have 0, 0 there. Next, this entry here must be a 1 by 2 matrix, so 1 row, 2 columns. So we multiply this 0 matrix to this one, that is a 0. And then this multiplied to this 0 matrix is 0. So again, the 1 by 2 matrix will consist of 0, 0 only. And then the last one, we multiply A21 to this. So that's 0, and then we just multiply this by this. Okay, so the 1 by 1, we will have a 1 by 1 result. So we have 2 times 1, that's 2, and then 1 times 3, that's 3. So plus, add them, so we will have 5. Okay, so it would be helpful sometimes if you have you will partition your matrices, especially if there are some 0 blocks there on your matrices. The next part is for your exercise. So you do the following, just practice. You find the products A, B, and BA given the following matrices. Okay, so this is the end of our part 1 in chapter 1.3. The next video, I will discuss the properties of these matrix operations. Sorry, here is the practice exercises. So again, find the products A, B, and BA given the following matrices A and B.